Think about what happens when you cook. You take raw ingredients, like flour and water, apply physical force to knead the dough, add heat, and change them into a meal. An industrial process plant works the exact same way. It's a massive facility designed to take raw materials and change them into useful global products. This flow starts with raw inputs, like materials and energy, moving through the center for a physical or chemical change. Finally, we get finished products. Every machine inside exists to either move physical materials or manage the changing energy. Imagine trying to install a massive new oven in a tiny 100-year-old kitchen. You must work around existing walls, old plumbing, and outdated wiring. Engineers call this a brownfield project, and it forces a lot of compromises. The alternative is the engineer's dream, a greenfield project. Unlike the messy constraints on the left, this blank slate on the right offers total freedom to arrange equipment perfectly and build a complete safety system from the beginning. Engineers use two primary machinery categories. On the left, static equipment has 0 moving parts, safely holding materials under pressure and managing heat flow. On the right, rotary equipment uses powered moving components to provide the physical force that pushes materials through the plant. It's a simple division of labor. The static equipment stays still to handle the energy, while the rotary equipment spins to move the materials. This shell and tube heat exchanger perfectly exemplifies static equipment. It moves heat between two liquids, one flowing through the outer shell, another through the inner tubes. Crucially, these solid tubes act as an impenetrable wall, allowing thermal transfer while keeping the fluids completely separate. Because every process uses radically different chemicals at different temperatures, you can't just buy these off a shelf. Each one is custom built for the specific environment where it will be used. Rotary equipment is where the plant gets its physical power. Think of massive industrial fans staying in constant motion to keep things moving. Selecting a fan requires two specific numbers. First is flow rate, shown on the top dial, representing the total volume of material moving every hour. Second is pressure, representing the amount of force required to shove that material through the plant's pipes. Selecting the right machine requires a perfect balance between that volume and force, while accounting for the natural friction inside the pipes. Engineers map the battle between plant resistance and machine power using this graph. The ultimate goal is hitting the best efficiency point, the glowing orange dot in the center. Operating here saves massive electricity, while missing it burns excess energy and rapidly degrades equipment. How do engineers plan a massive, flawless plant like this from an empty lot? They use a secret. They start with the finished working plant and then engineer the timeline backward. Looking at this diagram, they start at the right with final installation, then move left through manufacturing and design, back to the first blueprint. You can only perfect the very first plans if you have already visualized the successful finished plant in action. Designing backward on a blank slate allows for built-in safety. This shield shows safety split in two. On the left, ensuring machines stay strong and don't fail under pressure. On the right, protecting the workers. These protections are built directly into the design. This comes down to 3 rules. First, successful engineering is a reverse timeline, starting with the end goal. Second, long-term efficiency is pre-calculated by matching every machine to its best efficiency point. And third, safety is a non-negotiable part of the very first blueprint. By following these rules, engineers can build a safely transforms raw materials into the power and products that drive our lives every day.